going to be shifting gears. Earlier, we had looked at how coordinate geometry, work, especially focusing on some linear equations. But today, what we're going to do is we are going to start with word problems, okay? And we are going to see how word problems can be solved, okay? So the focus is going to look at some examples. So first of all, what we're going to do is we are going to look at the keywords that indicate how the problem is supposed to be addressed and what sort of mathematical operations each of these words represents, okay? And then we're going to start from there, okay? All right, okay. So the first thing, as with any mathematical operation, is how to understand what each of these represents. So first of all, let's say, looking at the basic mathematical operations, we have got the addition, subtraction, multiplication, division, as well as equality, okay? So the keywords to look out for each of these is, for example, if we notice that the statement mentions more than, some, or increased by, okay? So this, in all likelihood, refers to addition. So sometimes the context might be tricky, but we're going to start with the basics. So in all likelihood, these keywords represent that an addition operation has to take place, okay? And so for example, for the subtraction, what we get is if the keywords being mentioned are less than, minus, difference, okay? So particularly this keyword, the difference, okay? So this indicates that the two quantities need to be subtracted. And in a lot of cases, the order of subtraction matters, because sometimes if you subtract a greater number from a smaller number, you might end up with a negative, you are going to end up with a negative result, okay? So we have to make sure that in subtraction, the order of the quantities is also preserved, okay? And then there is multiplication. This is often indicated with the terms times, or sometimes it is mentioned as maybe twice another quantity, or thrice, or four times, which indicates that a multiplication operation is taking place over here. And for division, we get the per, so two quantities. If two quantities are mentioned and the relationship between the two is being mentioned, so it is often mentioned that this quantity per this quantity. For example, let's say in a mixture of things, we say 2 grams of salt per 10 grams of flour, something like that. Or, for example, it could also be mentioned as out of, so 3 out of 4 times. So that means that this is a division operation. Or it could be explicitly mentioned as a quotient, okay? Finally, if, when the equality is supposed to be ascertained, that is usually extracted from is, or equals to, or results in. So these are the things which indicate that, this is the result of a mathematical operation. So, the mathematical operation equals to this quantity. So these are the particular keywords for operations and how we are going to translate them into different mathematical operations, okay? So for the inequalities as well, so the word problems can, let's say, involve both the equalities and the inequalities. So the standard mathematical operations could also result in an inequality. So for example, the example could state that the sum of these two must be greater than this value. So greater than means that there is an inequality involved over here. So more than or exceeds, so the sum of A and B always exceeds this. This means that this is always greater than, okay? So the less than is again fewer than or is under a certain threshold. So an A and B is always results in a quantity under this value, or less than this value, or fewer than this value. So this indicates an inequality as well. So when we're talking about greater than or equal to, so that is at least. So for example, we say that one person could at least work this much. This indicates that the amount of work being mentioned is a minimum threshold. So the value is either equal to or greater than this threshold. So it's either minimum or no less than. So no less than also into, results or is translated into at least. So similarly, at most also results in an equality, and that is represented by maximum or no more than. So if you have the word no more than, that also means that the value or the mathematical operation results in a maximum or equal to this particular value. So either it's maximum or no more than, okay? We're going to look at a few examples which are going to clarify these mathematical operations as well as the use of these keywords as well, okay? And finally, what we intend to do is the word problem provides a real world a problem that needs some mathematical operations to be solved. So in order to do that, we are given various quantities that are unknown. And how do we solve them is by assigning variables to various quantities. So if we have a bunch of different quantities and we don't know them, so what we then do is we assign variables. So that's in fact the first step, that we have to identify which quantities are involved and assign variables to them. Secondly, once the variables have been assigned, next we want to do is we want to establish the relationships between different variables as stated per the keywords that we have already seen. And finally, the important thing is that once we have identified the results of various quantities reflected by the variables, we have to understand which of these variables is actually required by the question. So if you're given two or more quantities, so you're going to be asked for either of these three, any of these three quantities, or maybe a sum of these quantities, or a difference of these quantities, or maybe even a comparison of these quantities, or even simply the result of those quantities. So we have to understand what the question is asking of us. So it's whether it's the quantity A or B or C, which quantity is being required. So we have to understand, so that sometimes what people do is, even though they have calculated the correct answers or correct values for all of these variables, the answer they're going to input in the provided field might not correlate with the one that is being asked for in the question. So we have to understand which variable is being asked for, okay? So I hope that this basis is clear, because this is applicable for any sort of word problems, whether they are related to any particular domain, whether that is algebra, that is geometry problems, or that is data analysis. That is the start of these steps that we've just gone over. They provide the foundation of solving any word problem. Okay, so with this out of the way, what we're going to do is we're going to start with the simplest kind of word problems, which involve one quantity that is unknown. So this is a one variable problem in which the variable is going to be assigned to the unknown quantity, and that is the quantity that we are going to be interested in finding out. So what we're going to do is we are going to translate the word problem first, understand what it requires. We're going to identify which quantity is the unknown. So we're going to assign the variables to the unknown quantities. And then we're going to set up the equation or the expression that relates to different quantities as well as the unknown quantity together. And then we're going to solve, okay? Right, so with this out of the way, let's take a look at this example, okay? So the first example is Mary is 8 years older than John, okay? The sum of their ages is 30. And how old is John, okay? So first of all, what are the unknowns for us? The unknowns for us is the age of Mary and John, okay? So there are two individuals and their ages are unknown. So first thing is that we have to identify which are the unknowns. So Mary's age is unknown, and then John's age is also unknown, okay? And then the first statement indicates that Mary is 8 years older than John. So there is a difference of age of 8 years between Mary and John. And this also tells us that Mary is the older one. So if we were to subtract John or John's age from Mary's age, the result would be 8, right? Or if we were to add 8, this value, to John's age, we would get Mary's age, okay? So let's kind of translate that into a mathematical expression, okay? So the first thing is Mary's age. Let's assign the variable. So Mary's age is, let's call this as M, okay? Oh, okay, great. Right. Okay. And then let's call John's age as J. All right. So now we have two variables. The best way to assign variables is, to assign them, these characters, these alphabets, which most closely related to the quantities themselves. So in this particular case, Mary is M and John is J. So now we know that Mary is M and John is J. Okay, so that avoids confusion down the line when we are considering which one to answer. Okay, right. Okay, so first of all, Mary is 8 years older than John. So what does that mean? Does that mean M plus 8 is equal to J? Does that mean this? If we say Mary is 8 years older than John, no, this does not mean M plus 8 is equal to J. This actually means that Mary is 8 years older than John. Okay, so it's John's age plus 8 is actually Mary's age. Why? Because Mary is the person who is 8 years older than John. All right. So if I was to write it in another way, it would look like Mary, if we reduce Mary's age by 8 years, that would become John's age, right? So the first thing is that we have Mary is 8 years older than John. So John's age plus 8 gives us Mary's age, right? And the second thing that we're given in this particular case is Mary and John's age together sums up to 30, right? So Mary and John's age sums up to 30, right? How's that? That is told us over here in the second last sentence that the sum of their ages is 30, all right? So the sum of Mary's age plus John's age is 30. And now what we're supposed to find out is how old is John? Okay, we are not supposed to find out Mary's age. We might have to do that as an intermediate step, but we only want to find out John's age, right? So let's say, how do we do that, all right? So in this particular equation, we can do that by substitution method. And as we've already seen in substitution, what we do is we try to isolate the variables on one side of the expression and then try to plug in maybe this value of M over here. All right, so how we're going to do that is, let's say M is equal to 8J, 8 plus J. And so if we plug in this value over here, right? So we're going to have a single expression that is going to look like 8 plus J is equal to 30, right? So now we have a one expression in one variable. So the only variable that is involved is J, right? So now what do we get? We get, let's take the constants to the other side and let's keep the variables on one side. So if we add J and J, so we get 2J. And then if we take 8 to the other side, we're going to get 30. And because we're going to take 8 to the other side of the equality sign, we're going to reverse the sign of 8, which is positive over here. So we're going to make it minus. So 2J is equal to 30 minus 8. And then 2J becomes 22, right? And then if we divide both sides by 2, we're going to get J is equal to 22 over 2, which is 11. So J represents John's age. So, and we are asked about John. So John's age is 11. Okay, so look at this expression over here. I'm going to start this quickly, again. So look at this expression over here. What we do is, we plug in, this expression, M is equal to 8 plus J. And we say that M is equal to this, and there is an M appearing over here as well. So instead of writing an M over here, we just write 8 plus J instead of the M. And then we look at this expression. So we have 8 plus J is equal to 30. So now there are two J's which are being added. So we can, add the similar variable. So if I had A plus A plus A, that would result in, 3A. Can you point out? So for example, let's look at more simpler examples. So this particular example was the first one that indicated, how, let's say, different word problems may be solved. Let me just quickly give you an example which enables us to look at, examples with very simple scenarios, okay? So let's look at this particular example. Okay, let's take a look at this example. Okay, right. Okay, let me again do that. Right. Okay, let me do that really quickly if you have joined once again. So first of all, what we did was we assigned variables to the two quantities that are unknown. So in this case, that is Mary's age. So we assign M to that. And John's age, we assign J to that. All right. So, okay. So first thing is that we say that Mary is 8 years older than John. Okay. So Mary is 8 years older than John. And we want to find out two things. So Mary is 8 years older than John, and the sum of their ages is 30. So the first thing is Mary is 8 years older than John. We can do back solving as well, but in order to do that, we need to be able to make sense of the word problems first. And that is why, first of all, what we're trying to do is make sense of how the problems are going to be presented to you. And then we are going to take the back solving, which is kind of like starting with the best guesstimate. Like we are given 5 values, and we can assume one value. And then we can say that, okay, if this was John's age, and how old is going to be Mary, and then if we add these two, do we actually get 30? Yes, we can do back solving as well. So this is called back solving. But what I want you to first grasp is how word problems are translated into mathematical expression, so that our estimates are, say, an educated estimates. We don't want to go over all 5 of them. So if we have a better sense of how word problems were translated into a mathematical operation, that would eventually lead us to better guessing. Okay, so first of all, Mary is 8 years older than John. So for example, if let's say John was 5, what would be the age of Mary? Mary would be 13. Why? Because Mary is 8 years older than John. So if John was, say, 10 years, Mary would be 18 years, again, because Mary is 8 years older than John. Okay. Right. Okay. So in this particular case, what we do is we say that Mary is equal to John's age plus 8. How do we do that? We found out by this, because John's age plus 8 is, M is equal to J plus 8. And then the second thing is that if we sum both their ages, we get 30. Now we have got, an expression which tells us what is Mary's age with respect to John's age, and which also tells us that what is the sum of Mary's and John's age. Okay. And now what we can see is that this value for the variable is already isolated on one side. So we don't see another variable on this side. And this variable M is already described in terms of everything else in the expression. So what we can do is plug this value of M over here. Okay. And so this gives us, if I plug this value over here, so this gives us J plus 8 plus J is equal to 30. Right? So J plus 8 plus J is equal to 30. How do we get that? We got that by substituting the value of M by J plus 8, because M is equal to J plus 8. So we substituted M as J by J plus 8, and we got this expression. Now, if there are 2 J's, if there are the same variables, those might be added. Okay, so in this particular case, 2 J's means J's plus J is equal to 2J. Okay, and we take the constants to the other side. So if we take this constant to this side, so we've got 30 on this side already, and then because this 8 is being added over here, it is going to be subtracted on the other side. So we've got 2J is equal to 30 minus 8, which implies 2J is equal to 22. Okay, and then if we divide both sides by 2, we get 22 by 2, which is 11. All right, so this is your answer for this particular question. Okay, I hope this much is clear. Okay, let's move on to another example. And as we solve, you're going to see, things getting more and more clear. Okay. All right. So here's another example. Okay. A pen costs twice as much as a pencil. Together, they cost $4.80. What is the cost of the pencil? Okay, so let's see over here. So we've got a pen. Let's assign this as P. And then because this is also starts with a pencil, it also starts with a P. Let's not assign the same variable to this, but because this is a different quantity, we assign this variable as N. All right, so now we have got two variables, P and N. Okay, and now first of all, the thing is, what is the relation, the first relationship between P and N? So we say that pen costs twice as much as the pencil. So if the pencil was Right. I'm sorry about that. Let me quickly do that. I forgot to unmute myself. Right. I hope you can hear me now. So a car rental company charges a fixed fee plus 20 cents per mile. If the total bill is $1.50 for 200 miles, what is the fixed fee the company charges? So what is unknown to us is this fixed fee. All right. So this fixed fee, and what is told to us is the total bill. All right. So let's first assign this value to the total bill. So let's call it T. All right. And this T is 50. The total bill is 50. All right. And how did we arrive at this total bill? We were supposed to pay some fixed fee plus some cost per mile. So let's call this as C. So what is the total cost? The total cost is equal to some fixed cost plus cost per mile time the number of miles itself, right? And so this is, again, why? Because this is your cost per mile. So for every given mile, for every mile traveled, you're supposed to pay this much. And if you want to find out the total cost for the miles that we have traveled, we're going to multiply this cost per mile times the total miles that we have traveled. And what is the number of miles in this expression? The number of miles is 200. Okay. So the total cost is the fixed cost plus what is the C over here? The cost per mile. The cost per mile is 20 cents. So 0.2 times what is the number of miles that we have traveled? That is 200. And if we were to plug in the value of the total cost as well, that is 50. Okay, so now this is one expression which has only one unknown, which is F, which is the fixed cost. So what we do is we isolate this fixed cost or this unknown variable on one side, and we take all the constants to the other side. So let's do that. We're going to, and what is the result of this? So 0.2 times 200. So this is 40. Okay, so this is 0.2 times 200 is 40. Okay, and so now we have the expression 50 is equal to F plus 40, right? And then if we take 40 to the other side, because it is being added over here, so it's going to get subtracted from 50. So 50 minus 40 is equal to F. And then this implies that your F is equal to 10. Okay, so we have identified, so the first thing was identifying what is being asked. So we assigned a variable to this quantity, which is the fixed fee. Then we discovered that there is a cost per mile as well. So we assigned this variable, and we were given both the total bill as well as the number of miles that we have traveled. Okay, so using those, we were able to do that. If we were to suppose, for example, say that could we do some other sort of trickery to maybe arrive at this earlier? So if we said, for example, if we assume that the fixed cost is 8, right? If we assume that the fixed cost is 8, what would the remainder, which is going to be 50 minus 8 is equal to 42? Is the number or is the cost associated with the miles that we have traveled come out as 42? No, because we were supposed to get this as 0.2 times 200, which is 40. Okay, so 8 wouldn't fit. If you were supposed to do the same thing, assume that the fixed cost is 5. So 50 minus 5 is $45. So for the number of miles that we have traveled, is the total cost equals to 45? Again, that would be incorrect. Okay, so we can assume this as well, but going for the assumption or back solving, we always using the best estimate is not always the right approach. Okay, sometimes it's easier to actually build up this sort of a mathematical expression. So what I have done was maybe to explain this, I've done this as an additional step. Instead, what we can do is directly plug in the values and with the unknown, and that would be a simpler approach. Okay, moving on. Right. I hope that so far this is clear what we're trying to do and how we're trying to decipher the statement of the word problems. Moving on. So now we have a statement which indicates that the cost of 3 identical movie tickets is less than $30. Okay. What is the greatest possible integer price per ticket? Okay. So this is important. What is the greatest possible integer price per ticket? Okay. And so the cost of 3 identical movie tickets is less than 30. What does this mean? Okay, so if we're supposed to look at this in isolation of the second statement, it could be that the cost of one ticket could be $1. Okay, because 3 tickets would mean that the total cost is $3, which is again less than 30. Okay, it could be $2, which means yeah, absolutely, which would mean that the cost of 3 identical movie tickets would be $6. All valid options. But the second statement tells us is that what is the greatest possible integer price per ticket? So we want to find out the greatest possible value associated with each of those movie tickets, which results in 3 tickets costing for a total of less than 30. Okay, so if we were to do that, so something which is the movie ticket price, okay, let's call this as P. Okay, the movie ticket price, let's call this as P. So there are 3 tickets, so 3 times P, okay, and it should be less than 30. 3 times P should be less than 30. So some number which should be multiplied by P should result in 30. P could be 1, 2, 3, or 4, okay, but we want P to result in such a way that this becomes closest to 30. 1. And second is this value over here. P should be integer. So for example, I could multiply this with, say, I am sure that most of you would have arrived at the answer that if we multiply P with 9 or with 3 with 9, we get, if we assume that the value of P is 9, so 3 times P is equal to 27, right? So, and if we were to say multiply this with 9.5, you would get 28.5. Okay, this is again closer to 30. But what does this violate? This violates this condition that the ticket price must be an integer value. So decimals are not allowed. So if we were to do something like this, so 3P is less than 30. This is something that we have, this is something that we have also, done this when we were doing our coordinate geometry, that we can convert this into a boundary. Again, not confusing you for this, but for those of you who want to maybe, learn just the mathematical fundamentals, if we were to make this into an equality, so 3P is equal to 30, right? So P is equal to 10, dividing both sides by 3 gives us 10. But what we want is, in this particular case, what we want is our movie tickets to be less than 30. So what is the next integer before 10, or the smallest or the closest integer, which is less than 10, which that is 9. So the result of assigning the value of 9 to P is going to result as the next closest value to 30. And that is what makes 9 as your valid option. Okay. So that is why it is, say, very crucial to understand what the statement is asking us. So if we were, just the statement state that greatest, less than is not less than, but less than or equal to 30, then, C would be the right answer. Why? Because 30 is a valid option now. But now what we want to do is we want to keep the prices of 3 identical movie tickets less than 30. No, this means that, for example, the greatest possible integer. Okay, so as I said, your original expression is 3 tickets should cost less than 30. The cost of 3 identical movie tickets is less than 30, right? Let's, again, just for clarity's sake, let's just forget the second part, for now. Let's just focus on the first part, right? So the first part states that the cost of 3 identical movie tickets is less than 30. So if we had 3 tickets, they should always cost less than 30. So if I assign, let's say, P is equal to 1, so the 3 tickets would cost $3, right? Which is less than 30, perfectly valid. If I assign P the value of, let's say 4, okay? If I assign, say, P is 4, then 3 times P would be equal to 12, and 12 is less than 30. So again, P by 4 is also perfectly valid if we are just looking at the first part of the question. But then, what does the second part of the statement tells us? The second part of the problem tells us that we have to find out the greatest value for P, which can be assigned to P, so that the result of 3 tickets remains less than 30, or so that this condition is not violated. So 3P less than 30, and we are to assign the greatest value to P such that this product remains less than 30. Okay, I hope you understand the point that I'm trying to make over here. Okay, that this second part is what tells us the restrictions on P, that P has to be as high as possible so that the value of 3 tickets is as close to 30 as possible. That's the first condition. That's your first condition. The second condition is that, fractions or decimal numbers are not allowed. So it has to be an integer. It has to be an integer. So 8.5, 9.5, 9.7, 9.11, these might bring you closer to 30, but they're not valid choices because the ticket price has to be an integer value. So that is why the only possible value of P that brings this product as close to 30 as possible is 9, because 3 times P is 27. If we assign P as 10, it becomes 30, but we want the price of these 3 values strictly less than 30. A is also right. As I said earlier, as I tried to mention earlier, all the values of P, for which this product results in a value less than 30, those are all valid options if we just look at the first part of the problem statement. But the second statement tells us that what is the greatest possible integer price per ticket? The greatest possible integer price per ticket such that 3 tickets together would cost less than $30. Okay, but yes, if we were looking at the problem statement, separately, if we were looking at the first separately, yes, 8 and 9 would be valid, but we have to take this problem holistically. We have to take both these statements together. Okay, so if we do that, we say that we have to find out the greatest value which can be assigned to P, which taken as the product with 3 results in a number, less than 30, right? So for example, if I say find a number less than 10, okay, I'm going to go with a very simple number, right? Find a number less than 10. Okay, you could find any number, say 5. You could say 5.5 because I haven't mentioned an integer. You could even say -5 again because I have mentioned a number that is less than 10. So any number that is less than 10, right? So any number less than 10 is valid. But if I say find the greatest even value less than 10, what would that mean? That would mean that you are supposed to find an even value which is less than 10, the greatest even value less than 10, right? Yeah. Okay. So again, continuing with my examples, the greatest even value less than 10 would be 8. Okay. Because the next even value is 10 itself. But we don't want to reach 10. We want to stay less than 10. Okay. So there's a strict less than condition over here. As I said, once we try to say, convert this inequality, so this is a strict less than. So we cannot have the cost of 3 movie tickets reaching 30, right? We were doing the pencil and the pen example, but I wanted to do something maybe a bit simpler. We will do that later on as well. That's over here. But let me just first try to explain how to convert these problems into mathematical expressions. Okay. So I hope this is clear now. So I just want to move on. Okay. So in one of the previous examples, just before last, we said that we were given the total price, and we were given a fixed charge, and we were given the number of miles, and we were asked to identify, if we were asked to identify the fixed price. Okay, this is kind of the same problem, but in a roundabout manner. Okay, so what does this tell us? What is this asking of us? A taxi charges a $5 flat fee plus $2.50 per mile. If you have no more than 30, how many miles can you travel? Okay. Okay. Let's try to focus over here first. And as I mentioned, maybe I'll try to find maybe a couple of minutes before we call off the session to address your concern as well. Okay. So looking at this problem. Okay. Right. A taxi charges a $5 flat fee plus $2.50 per mile. If you have no more than 30, how many miles can you travel? Okay. Right. So what we want is we don't want our total bill to exceed 30. All right. So out of 30, okay, $5 are going to go towards your fixed fee, and the remainder, which is $25, are going to go towards your travel cost. Okay. And so each mile, so now you have effectively how many? You've got $25, okay, for the miles that you can travel. So $25, okay. And what is the cost per mile over here? That is $2.50. Okay. That is $2.50. So we've got 25 miles, $25 in total, and we have the per mile cost as $2.50, and we want to find out how many miles you can travel. Okay, if you have no more than 30. Okay, if you have no more than 30. So again, here's the thing: you don't want your total bill to exceed 30, and out of these $30, $5 are going to go towards your flat fee. Okay, and the rest, which is these $25, they will contribute to how many miles you can travel. So this is $25, and now we're given the cost per mile, which is $2.50. Okay, so let's start counting the miles that we can travel until we reach $25. Okay, so 250 times, one is the number itself, times two is $5. Okay, times 4 is $10, and then times 8 would be $20. Okay, right. So you see how I'm going about this? So I said that, okay, if I travel one mile, the cost is going to be $2.50. If I travel 2 miles, the cost is going to be $5. And I want, the maximum number of miles which can, make full use or as close of a use of these $25 as possible. Okay, so I keep on adding the miles. So first, mile one, $2.50. I have a lot of dollars to go. So if I travel 2 miles, I have to pay $5. If I travel 4 miles, I will have to pay $10. And now if I double this, because for 4 miles it is $10. So for the next 4 miles, again, it's going to be $10. So for 8 miles, the price is going to be $20. Okay. And now if I add 2 more miles, okay, so I am going to add +2 and +5 over here. So that would be 10 miles and $25. So if I travel 10 miles, what I can do is I can spend $5 towards the fixed fee and $25 in their totality towards 10 miles. Okay, so how many miles you can travel? You can travel 10 miles. Okay, I hope this is clear. So this was the same problem, but given in a roundabout manner, that you were given the total bill, but you were not supposed to exceed this amount. So what we did was we can do that as well. We can do that as well. Yeah, 25 by 2.5. Yes, this also gives you 10, absolutely. But what this makes is that this kind of converts this into a rates problem as well. And we haven't covered that. We're going to cover that in one of our upcoming sessions, because these word problems, relate percentages, rates, a lot of proportions. So I just wanted to stay clear of covering rates for now. But yes, if you identify that this is your total cost, okay, and this is the cost per mile. So simply what you can do is total times mile by total. So you cancel this out, you cancel the units out, and you will be left with the units themselves. So you can do that. But as I said, that would take us into the realm of rates, which we haven't really explicitly covered just yet. And that is why I didn't want to use this method. I hope that answers your question. Okay. So, right. Again, this is a rates question. Okay. But this is, again, what we want to emphasize right now is how to interpret the statements. To qualify for a marathon, you must run 10 kilometers in less than 50 minutes. Okay. So this is the total distance, and this is the total time that is allocated to you. What average speed must you exceed? Okay. Here's the funny bit. Must you exceed? So what we want to find out is that this is the minimum. So you can maybe cover 10 kilometers in, say, 40 minutes, right? But what would be the minimum speed dropping below which you will not be able to cover 10 kilometers in 50 minutes? Okay. So first of all, let's see. So you're supposed to cover 10 kilometers in 50 minutes. Okay. So how should we go about this? So if we simply do something like this, okay. So let's say if we were to do 10 kilometers in 50 minutes, what would we want to do is say we divide this 50 into 10 equal chunks. Okay. Again, I'm trying not to get into the rates part, but it would be much simpler if we do this by rates part. I don't just want to get into that domain right now. That's why I'm using this alternate. So if we do that, let's say we assign, why I'm doing this is because I want to cover 10 kilometers. So let's say this is my time. This is my 50 minutes of time. Okay. And I convert this into 10 equal chunks, meaning, for every chunk, I am covering 1 kilometer. For every chunk, I am covering 1 kilometer. So that means that I am covering, this is 50 divided by 10. So each of this chunk, this is 5 minutes, right? So because I've converted this into 10 equal chunks, so each of these chunks is 5 minutes, right? And in 5 minutes, what I'm doing is I am completing 1 kilometer, right? So my speed right now is 1 kilometer over 5 minutes. Okay. Okay. Let's just solve this for now, and then let's see how we can arrive at that problem. Okay. So I am supposed to cover, if I want to cover 10 kilometers in 50 minutes, I am supposed to travel 1 kilometer in 5 minutes. And so what would be my speed per minute? So this is 1 kilometer. So I cover 1 kilometer in 5 minutes, right? So I'm covering 1 kilometer in 5 minutes. Okay. And so how much distance would I be covering in, say, 1 minute? Okay. Here I go again. Okay. So I have 1 kilometer. So this entire quantity is 1 kilometer, and I divide it into 5 equal chunks. Why 5 equal chunks? Because I've got 5 minutes. So if I want to maintain a constant speed, I need to cover the same distance across 5 chunks so that I cover the entirety of this 1 kilometer. Okay. And so what times 5 would result in 1? Okay. So I have to cover 0.2 kilometers over here, 0.2 kilometers over here, 0.2 kilometers over here, so on and so forth. So if I cover 0.2 kilometers in every chunk, which is 1 minute, I'm going to end up covering, 1 kilometer in 5 minutes. Right. So exactly. Right. So now this is, the speed 0.2 kilometers per minute. Okay. Is your speed if I, have to cover 10 kilometers in less than 50 minutes. Okay. So if I want to cover 10 kilometers in 50 minutes, I have to run at a speed of 0.2 kilometers per minute. Okay. Yeah, so this is the speed that I must maintain or travel faster than. So this is going to be my baseline. So this is my average speed that I must exceed. Why should I exceed? Because I don't want to do that in 50 minutes. I want to do that in less than 50 minutes. So my speed should be greater than 0.2, maybe 0.21 or 0.22, but anything equal to or less than 0.2, and I won't be able to cover this 10 kilometers distance in 50 minutes. Is that clear? I hope that I'm trying to, again, as I said, as I mentioned earlier, because I haven't really explicitly covered the rates part. So I want to kind of, stay away from solving it using the rates method. Yeah, absolutely. So our speed must exceed 0.2. So what we want to find out is the boundary over here. This is our boundary. Okay. Yeah. And why this is our boundary? Because we want to cover the distance in less than 50 minutes. So let's say 49 minutes and 59 seconds. That's valid. That's a valid time because we want to do it in less than 50 minutes. So that's only possible if we exceed the speed. If our speed is greater than 0.2 kilometers per minute, we would be able to beat this goal, which is covering 10 kilometers in less than 50 minutes. Okay, so this is our speed must be greater than this value, must be greater. We could run, let's say at 0.4 kilometers per minute. Okay, we could cover, say, yes, exactly, because the relationship between speed and time is different. The faster you travel, the lesser time that you're going to spend. As I said, why I don't want to, kind of go into the rates is because we haven't really covered that. But still, well, how we did that was by identifying what we really wanted to do. So if we were to, for example, maintain a constant average speed, what we can do is, first of all, divide the entire time into the distance. And they said, this is the basic chunk of distance that we must cover in the smallest unit. Okay. And then take that chunk and further divide into the number of minutes that we get. And we get this, the answer in the required minutes. In these required units. Okay. Let's do one last question before calling off this session. Okay. And this is, again, a word problem. So you have to understand that before jumping in, we have to read the statement clearly, what the statement is asking of you. Okay, there could be multiple requirements, but what we want to understand is that what exactly is the statement requiring of you. Because if you don't do that, even if you identify the operations correctly, but you don't understand the relationship between different quantities, that would eventually end up in wrong answers. Yeah, I've seen some of your I've seen that some of your friends have already done that. So let me do that for the rest of the participants as well. a number is decreased by 4, okay? And the result, when multiplied by 3, is equal to 27. What is the number? All right, let's call this number as n, because this is the quantity that we don't know, right? So the number is decreased by 4, okay? So this means that the number is decreased by 4, okay? By decreasing, it means that we take n and we subtract 4 from it, okay? And then the result, this value, n minus 4, when multiplied by 3, if we multiply this with 3, so n minus 4 times 3, so the result is equal to 27, right? So let me write this down neatly for you. So you've got n minus 4, which is the number decreased by 4, and then multiplied by 3 results in 27. Okay, so first of all, this is, let's try not to do that arithmetically, but let's try to do that directly. What number times 3 would give you 27? That would be 9. We know that 9 times 3 is 27, okay? But what is 9? 9 is actually the number decreased by 4, okay? So this entire thing in brackets, this must be 9, because this times 3 gives you 27. So the number decreased by 4 is actually 9. So what we do is we take 4 to the other side, or we simply increase this value by 4 to get back to the original number. So 9, n minus 4 is equal to 9. We take 4 to the other side, and we get n is equal to 13, right? Yeah, absolutely. We can do that as well. The alternate way, that is also valid, okay? But this would be kind of directly translating the statement into the most direct form of mathematical expressions that is possible, okay? So I hope that this one is clear. So what does this tell us is a successive mathematical operations. First, decrease the number by 4, then take its product with 3, and that gives you a result. Absolutely, options will also reveal the story. So let's quickly do this by back solving, okay? So let's do this by this value, okay? Let's assume that the number is 15, okay? If we were to reduce this value or decrease this value by 4, what would we get? We would get 11, and 11 times 3 is 33, okay? So this means it's not equal to 27, which means that if we jump over here, this is going to take the number even farther. So let's take a step backwards, okay? And then we have this 13. This is the value of the number itself. If we reduce 13 by 4, we get 9. And its product by 3 gives us this value, which is 27. So this is correct, okay? So you can do it both ways. You can jump directly to, formatting or formulating a mathematical expression, or you can do that by taking the options and back solving them. So back solving is exactly this: take the answer, back solve if it validates the conditions provided in the statement itself. So that is back solving. You're not starting from the statement going towards the answer. You're assuming an answer and back solving it through the conditions and identifying whether all the conditions are met. So in this particular case, if we were, let's say, if you've got a number that successively goes through some operation, you take an option and you perform that operation in a different manner or in the reverse order, and you will get the answer, okay? So yes, this kind of is an example of how options can be used to back solve a given word problem, okay? So with this, we come to the end of our first session.